Okay, today we are going to be talking about thermochemistry. Thermochemistry studies how the energy that is either absorbed or released from a chemical reaction, how that changes the temperature of what the reaction is taking place in. So there's some different formulas that we need to know for doing thermochemistry. This first one I first have here written out in words, and then have it written out just in symbols, as I'll mostly use it because it just takes time to write all those words down. So these two right here go together. Okay, so one's just in words and one's in symbols. Okay, so notice that we're going to be using this delta. Delta in science just means that you're going to take the final minus initial. So in thermochemistry, it's not the temperature that's important, it's the amount of temperature change that's important. And because we're looking at temperature change and not actual temperature, we don't have to use Kelvin temperature like we did in gas law. We can use regular temperature. Okay? So that's one important formula. That first one relates how much energy is coming into or out of a substance. Okay. So the second equation we have here is about the amount of energy that's coming into or out of a reaction. Actually, I should just say into or out of a process, because physical changes can also absorb and release energy. Okay. Now, when we're doing problems, a lot of times we're going to be looking at like a combination of multiple materials. One thing losing heat and one thing gaining heat. And so because of the law of conservation of energy that says energy can't be created or destroyed, if we add up all the heats together, we're going to find that it adds to zero, so that this symbol here means the sum of something. So if you have all the different heats of things that are inside a closed system, one where it's not exchanging heat with the outside world, we're going to find that they all add to be zero. Okay? Put this in a little bit of different terms. If I only have two different things exchanging heat, one thing that's warm and is going to be cooling down, and one thing that's cool and is going to be warming up, or I can think of one thing that's absorbing energy and one thing that's releasing energy, I can kind of rearrange that sum up, and I would find that the amount of heat given off by the warm thing is going to be equal to the amount of heat taken in by the cool thing. And the reason for the negative sign is because in chemistry, positive means that it's taking it in, and negative means that it's giving it out. Okay, so let's just take these formulas and look at them in the context of the lab that you've already done. And so first of all, looking at why should water come to an average temperature between them. It seems intuitive, but from the formulas, why should it? And it's because that the hot water and the cold water, the heats have to be equal to each other. If they're the only things exchanging heat, whatever energy leaves the hot water should go into the cold water. And so if I substitute in those formulas that I had before, that MC delta T, if we put in the same amount of water, then the mass on both sides of these equations cancel out. If I put in, since they're both waters, this specific heat, which is something that's specific to each substance and has to do with how much energy does it take to change that substance by a certain amount of temperature, since they're both water, that's going to cancel out because it'll be the same. And so we'll find that the change of temperature on the hot water and the change of temperature in the cold water should be the same then. Okay. Now we look at, well, why don't they come to the same temperature? It's because you probably started the cold water in your container inside your calorimeter, and what we find then is that the calorimeter also has to be warmed up. So the hot water is going to cool down more than the cold water warms up, because there's additional heat that we have to figure into going to the calorimeter. Or if we started the hot water inside the container that they were mixed in, then we'd find that the cold water has to come up in temperature by a lot more, because it's going to try to be cooling down two different things. So a good calorimeter would be one that absorbs no heat at all, so it just doesn't interact. Okay. For the second one, why does the water change temperature so little compared to the metal? Okay, so again, we can see that the amount of heat leaving the water, or sorry, coming into the water, because the metal was hot, so the amount of heat coming into the water has to be the same as the amount of heat that's leaving the metal. Okay. Well, so again, we can plug in what we know about these substances, that mass times the specific heat of water times the temperature change of water is equal to what's coming out of the metal. Okay. Now, even let's say if we had the same amount of mass for metal and water, okay, water, so we'll just pretend like the mass is the same, so again we can cancel these m's out, so we can just focus on the c's and the delta t's. The C for water is 4.184, okay, joules per gram degrees Celsius, and this is a really important number. Okay, problems will just assume you know it, they won't give it to you. And for metals, it's generally under 1 joule per gram degree Celsius, oftentimes much under 1, so like 0.3. And so we'll find that the C for water is oftentimes on an order of like 10 times the amount that the specific heat for a metal is. So if this C over here for water is going to be equal to 10C from the metal, okay, then we'll find that the temperature change for the water is oftentimes going to be on the order of 10 times less, approximately, than the temperature change for the metal. Okay, so there's a big difference. So water actually has a very high specific heat because of the type of bonding involved between the water molecules. And it's very difficult to get those water molecules moving, okay, relative to each other. So you got to put a lot of energy in, so that leads to a high specific heat. For part 3, some of you probably found that as you added more of one substance, you got more of a temperature change, and some of you might have found that you didn't get more of a temperature change. So why might it not matter how much of a substance you added? Certainly, if you increase the amount of both substances, you're going to get more of a temperature change to some extent. But if you increase both substances, you also have more stuff you have to change the temperature of. So depending on how it was done, that might scale up the same way. Where if I double the amount of substance, it takes twice as much energy to change their temperature, so I might not get a change at all. If I only increase one substance, I might find that it has an increased temperature change, but I might find that it doesn't. Okay, so the amount of heat is related to the amount of moles that you use, but that number of moles has to be the moles of the limiting reactant. So let's say if you were adding more and more baking soda, but baking soda already was the excess reactant, so every time you were just using up the amount of vinegar that was there, okay, then it only mattered that you kept the same amount of vinegar each time. So as you add more and more baking soda, you can only change the temperature based on how much vinegar is there. Okay? And in fact, since you added more baking soda, since the amount of heat released, or actually in that case, the amount of heat absorbed is going to be the same, but now you have more stuff to absorb it from, then you might actually find that as you add more baking soda, the temperature change goes down because the baking soda is harder to change the temperature of as you add more and more of it. So that one, it might not be that straightforward because there's a lot of different things that can be taking place. Are you in fact changing the amount of the limiting reactant? If you're changing the amount of both, it's also that becomes harder to change the temperature of the entire system because you have more stuff to change the temperature of. So there's a lot of things that go into that one. Okay. So then, how does a reaction cause a temperature change, or why does that happen? Well, if you remember that when we're reacting something, what we're doing is we're rearranging atoms. Well, to rearrange atoms, that requires breaking bonds that already are there, and then making new bonds. So when we look at how much energy is absorbed or released by a reaction, it's just looking at the difference between how much energy is used to break bonds and released to make bonds. So when I break bonds, that does require energy. So to break this bond, if I'm looking at this is the reaction between 2 hydrogens plus 1 oxygen to make 2 waters. Okay. So I look at the total required. Okay, to break a hydrogen-hydrogen bond is 436 kilojoules, and I have to do that 2 times. And the total amount of energy to break an oxygen-oxygen double bond is 498 kilojoules. So in total, I have to use 1,370 kilojoules to break all these bonds. Then when I make bonds, every single one of the bonds here in these 2 water molecules will release 464 kilojoules as it's made. So the total amount released is 4 times 464 kilojoules, or 1,856. So again, we call a requirement, the amount of energy put in as a requirement, that's something that's absorbed. And so I'm going to call that positive, okay? And then I'm going to subtract what's then taken out or what's released, okay? So a release is a negative because it's going out into the system, okay? Just like when you're paying bills, it's a negative to you because that money is going out into the system. And so it's a total of negative 486 kilojoules taken out for this process. So looking at this, since this reaction releases energy overall, it's going to warm the surroundings, okay? Because energy is going to go out into the surroundings when this takes place. Or maybe not necessarily warming the surroundings, maybe that energy is used to do some work, like launching the little rockets that we did in the stoichiometry lab. Okay, so reactions in any processes really can be considered one or two things. They either can be called endothermic or exothermic. If you recall back to like when you were in biology, you might talk about like endoskeleton versus exoskeleton, or an endotherm versus an exotherm. Endothermic is something where it's taking energy into, so it's bringing energy in. And exothermic is one where it releases energy out. Okay? So, in an endothermic, more energy is required than released, so the surroundings lose energy and the surroundings have a decreasing temperature. Exothermic reaction is opposite. More energy is released than required. The surroundings absorb the energy and the temperature increases of the surroundings. So if we look at an endothermic reaction, we start at some amount of energy. During a reaction, you always have to add some amount of energy in to get to this immediate, and then you fall back down to your products. And you end up higher overall than where you started. And so that's where the taking in. For exothermic, you start somewhere in energy. Again, you have to go up first, then you come down much further, and so energy is given out in that process. Okay, so for endothermic and exothermic, remember that the change in temperature, so that's what this dT means. It means the temperature change. In an endothermic reaction will be negative, and in an exothermic reaction will be considered positive. The energy change of the reaction, or actually this is technically the enthalpy change, and we won't worry about the difference between the two, is the opposite. If I'm taking energy from the surroundings, making the surroundings cool, that means I'm going up in energy, so I'm positive. If I'm giving energy out to the surroundings, making them warm, giving them a positive temperature change, then I'm going down in energy. Okay, so that's why that is negative. So that's why they're opposite of each other when you look at the temperature change versus the enthalpy change. Okay, let's look at a couple example problems of the type of mathematical things that you might have to figure out. So the first one, what is the specific heat of a metal that changes from 100 degrees Celsius to 25 degrees Celsius, while in 100 milliliters of water that changed temperature from 23 to 25 degrees Celsius. So when we have two different substances exchanging temperature, we're always going to go MC delta T, and this is for the metal, equals negative MC delta T, this is for the water. So the metal has a mass of 35 grams. The metal's specific heat we don't know. The metal's temperature change is negative 75 degrees Celsius, okay, because it went down 75 degrees Celsius. On the other side, the water started up was 100 grams of water, since water has a density of 1 gram per milliliter. Again, it doesn't say this in the problem. You're just expected to know that water is 4.184 joules per gram degrees Celsius. And the temperature change of the water was up 2 degrees. Okay? So, we would take on the left 35 times 75 negative. We go over here, negative 2,625 times the specific heat. On the other side, if I take negative 100 times 4.184 times 2, I get negative 836.8, and then divide both sides by negative 2,625. And I get 0.32, and the units are joules per gram degrees Celsius for a specific heat. Next example problem. How much will a 100 gram sample of water warm if a reaction is carried out with 0.1 moles of reactant is used, and the enthalpy of reaction is negative 56 kilojoules per mole. So here I'm going to do that the moles, whenever I have a process exchanging heat with a substance, moles times delta H is equal to negative MC delta T. Okay, so this on this side is for the reaction, and on this side is for the water that we're exchanging temperature with. Okay, so on the one side I have 0.1 moles. I know my delta H is negative 56 kilojoules per mole, but you always have to put this in joules, so negative 56,000. Okay, so just like there is 1,000 meters in a kilometer, there is 1,000 joules in a kilojoule. Joules per mole, so then the moles will cancel out, equals negative. 100 grams of water, specific heat, again, not given to you, you just have to know 4.184 joules per gram degrees Celsius. And the temperature change is now what we're looking for. Okay, so again on this side I would get negative 5,600 joules, and on this side I would have negative 418.4 joules per degree Celsius times the temperature change. So if I divide both sides out by negative 4.184 joules per gram, or sorry, joules per degree Celsius. I'll end up with units of degrees Celsius. And so it would be 13 degrees Celsius. Okay, so hopefully you're able to get those sample problems to work out. You'll be working some similar problems tomorrow in class.